if they give you the temperature, there is a temperature compensation. If when you're doing the speed of sound lab, it is 30 degrees outside, let's hope that it is, right? Or 35 degrees outside. 37 is 98.6, right? So let's hope that it's 35 degrees out there, right? Okay. Keep in mind that the speed of sound is going to be a little bit faster than 343. Yeah. All right, are we ready for the next concept? The speed of sound for different substances, right? So air, there it is, right? Helium is a lot faster. It's the same elasticity for helium, right? It's the compression of it, but what do you suppose is true about the density? It's a whole lot less. That's why helium balloons float, right? So if you breathe helium and talk, do you suppose that makes your voice sound a little higher? There we go, right? Faster speed is higher frequency. Why is water so fast? It's not water should be slow because it's so much more dense than air. Or maybe it's like way more than air, you know what I'm saying? Okay, it's like, how is water more elastic than air? Well, just think about, basically it's the stiffness of it, the spring constant. If you were going to compress air, a cylinder of air, a certain amount, how much force would you have to exert? Well, some force, right? But imagine compressing water the same amount. How stiff that would be, right? Or some kids said it in another period, they said it really better than that. They said the water molecules are so much closer to each other so that any wave going through them is going to go so fast, right? Okay. And then steel is, of course, more dense than water, but it's also way, 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 way more elastic, right? This is kind of cool. So you know, this is my story, right? When I was in college, they built this brand new swim center called the Leonard Natatorium, which they tore down recently to build an even better one, right? Okay, and this swim center was 18 inches shy of the proper length of a pool. Isn't that sad? How long is a pool? 50 meters, and it was 18 inches shorter, and that's sad, right? So they built it, they couldn't have swim meets there, but here's the cool thing about it. On one side of the pool, there was a hallway, and if you walked down that hallway, there was a big glass wall. You could see the level of the water right there. So you could walk, if you were a coach, you could walk along, one of your swimmers could be swimming by, you could walk along and you could say esoteric things to them through a speaker system built into the water. They had these hydrophones and you could talk to somebody underwater, right? Yeah. And you could say things like, you need to flare your nostrils more, or something like that. I mean, I don't know, what do the coaches say? Something like that, right? You know, really, you're gonna get a hundredth of a second more if you flare your nostril when you strike the wave or something like that, right? You know, so they could say stuff like that. The reason that I knew this was not that I was a swimmer, it was that I wasn't a swimmer, okay? I had to pass advanced life saving to be a counselor at the camp where my girlfriend was gonna go, right? And this was a necessity. I had to be a camp counselor there, yes? Right? And to be camp counselor, you had to pass advanced life saving because it was a canoe camp, right? And on the first day of advanced life saving class at Capitol Middle School, junior high school, Capitol Hill, I forgot. Okay. Anyway, the teacher took me aside and she said, you know, you're going to fail. I can't pass you. And I go, why? She goes, well, you don't know your strokes. You have to be able to do crawl, you have to be able to do backstroke, you have to be able to do breaststroke. And I didn't know any of them, really. Because I'd swam all my life but never really learned how to swim, right? And so I was very sad, and I said, well, no, just give me a chance. And she said, no, you're not going to learn it in time. No. Every morning at 7 o'clock, I got up and I went down to the Leonard Natatorium, and I brought Mannheim Steamroller on cassette tapes, yeah? And I put it in their stereo, and then I patched their stereo into the system, the underwater hydrophones. And I listened to Mannheim Steamroller, which was somewhat more inspiring than the theme to Rocky. Right? I'm picturing this, right? The young woman who lived across the hall was captain of her swim team. Her work study was to be lifeguard from 7 to 9. Nobody at Macalester College was in the Leonard Natatorium from 7 to 8 o'clock, except me and her. And she gave me private swimming lessons because she was so bored, right? She showed me how to do the breaststroke. She showed me how to do everything, right? You know, and I was listening. I don't know. I passed. It actually, besides swimming, the other skill that's very handy for advanced life saving is wrestling. Let me just tell you that. Being a good wrestler is a sort of thing. We'll do these demonstrations at the end there because I want to move on. and show you this tricky little calculation. Whoops, not this one. This one. Okay. So, and the book likes to give you these problems. You hear the sound of an explosion through the water 1.42 seconds before you hear it in the air. Why is this? Travels faster through water. So if there's an explosion, say here, kapow, right? Or if somebody's like fishing with dynamite there and you're like here, right? I don't know why. Oh, there we are, right? You hear it through the air relatively later than you hear it through the water because it goes so much faster through the water, right? And then it's like, well, at 1.42 seconds, the more that time is, the farther away you are because the more it's like a race, right? The fast runners get farther ahead in a longer race. You know what I'm saying, right? But how do you figure it out? Well, you can mess with it a lot. Let me just show you how to figure it out, right? This distance is x. The time it takes the sound to travel through water is just x divided by 343, or whatever the speed of sound is in air, right? So the time it takes to go through the air is this. The time through the water, subtract that from it, right? That's what's 1.42. So this is the hardest one, is where you don't know that distance, right? Does that make sense? So this is the time it takes to go through the water or the air, right? This is the time it takes to go through the water. What if I switch those? Would I just have negative the right answer? Yeah, you know, so there it is, right? So I put the one with the biggest denominator as the thing that's, you know, first, right? How do you solve that for x? Can it be solved for x? It cannot even be solved for x. Can it? There's two x's. What do you do with that? Factor. Do you factor? Yeah, you factor. Good job. Okay. So I'm going to factor x out of that, right? Don't you love it when people do math like that? What's the next step? Do we divide by the parentheses? Yeah, there we go. All right. I don't know. I can't think. Can you think of a better way to do that? I can't. So the distance is going to be, take your calculator and try that one. So 1.42 divided by, bless you. Do you guys get like 639? So it's 639 meters roughly. Let's have you guys try another one of those. Not that one. Not that one. How about that one? This is a different one. It's the same kind of problem, but now I'm asking you for what the 1.42 is, right? That's the question that I'm asking, and it's not 1.42, obviously. And I'm telling you that x is 512, right? Take your calculator and see what you calculate. You could just do it. Do you get 1.14 roughly? 1.137 something. So 1.14 seconds is the time separating it, right? So those are tricky little problems. They're not the most important problems in the whole chapter, but there they are. And then, let's see, beats. Let's learn about beats. You guys ready to learn about beats? Yeah. Okay. If you play two notes together, 50 hertz and 60 hertz.